going to have a look today at A-level physics. We're going to have a look at this topic by topic, and we're going to have a look at motion. We're going to have a look at distance, speed, velocity, acceleration, and see if we can work out some of the laws of motion to do this. Right, I've got to help me here. My Pasco set up my wireless carts, which we can use to measure various bits and pieces like velocity and see if we can work out what happens. So let's have a go at trying to work out what these things are and look at some basic experiments to sort out how they all relate to one another. Our first thing we're going to have a look at is that of basically motion at a constant sort of speed, and that we're going to call velocity. Now, velocity and speed are words that students tend to mix up quite a lot, and from GCSE we know that speed is basically how fast we're going, and velocity is about how fast we're going, but including a direction. So we've got here magnitude and direction, and speed is only how fast, the magnitude. And we can work out that our speed, we know from elementary GCSE maths, is the distance divided by the time taken to cover that distance. And in exactly the same way, we can say that our velocity is also our distance in basically a straight line in a particular direction divided by the time. They're exactly the same formula to do the exact same sort of thing, really. So if we want to work out our distance travelled, then this is simply going to be rearranging the equation. Now, distance fools everyone because we're going to give it the letter S, and we're going to say that is the velocity times the time. Now, when we're getting something moving in a straight line, we get a nice distance. The only time we get a problem with this is when this is travelling in a circle, and we'll do more of that later. So what we're used to is trying to produce a distance time graph, and we have our distance and our time, and what we expect to see here is a suitable graph doing something. Let's see if we can actually achieve one of these things. What I've got then is my little trolleys, and they're already connected up to the software, and I'm just going to disarm this. We've got on here a little meter, and this little meter here detects its velocity in a particular direction. So what we can do is look at this, and if I push this in a particular direction, you can see the red lights light up, and if I push it in the other direction, you can see that the green lights light up. And Depending on its velocity, we get a number of chevrons. So if I push it hard, I can get 2. If I push it harder, I can get 3. Slowing down so it gets 2. If I go really fast, we can get more than that. Let's try again. And there's 5 going along. My trolley's actually longer than my bench, so it causes me a few problems, but we've got a nice long bench to do the work. Okay, we've got this basic idea then. This cart is electronic, so it can send back its data to the computer, so we can measure time and we can measure distance and we can draw a graph. So let's see if we can set this up ready to go. And what I'm going to do is I'm going to push this cart down from this end to the other end, and at the end here I've got some magnetic buffers. So if I push this now, we can see that it will actually return. So I'm going to try this experiment, but what we're going to do is we're going to, as well as visually watching this, what we can do is we can actually get the exact data sent to the computer. I've got here some special software. This is Pasco Capstone, and what we're going to do is we're going to try and draw a simple graph. So we're going to try and graph an equation, and I think I'll just draw a graph, it'll be easier. There. Right, now what I'm going to do is I'm going to choose what my axes are going to be. So this measurement is I've got my blue and I've also got a red trolley, and what I'm going to do with these is I'm going to choose my blue trolley, and I've got here various things that I can do, and on my blue trolley I'm going to mark in my velocity, and this is clever enough to work out there's going to have a time as well. So I can measure velocity, or I could measure distance. The software is actually very clever because we're going to record not only my velocity, I can record my position, and I can record my acceleration and all the forces involved. So we've got a time. Down the bottom here, I'm going to choose how often I'm going to take readings. At the moment, it's setting readings to be taken 20 times a second, and I could increase that or I could decrease that. I'm going to take it down to perhaps, let's say, 1/10 of a second. So every 1/10 of a second I'm going to take a reading of my position and the time. This graph can move around as we want to. It'll also scale as well. So let's set this to record mode and see what happens. We're going to do it a couple of times so you can watch it on the screen, this screen, and you can also watch it moving live as well with the camera. So we're going to do this. We can also get even cleverer with this software if we want to. So let's set here record going. It's not doing anything. We'll push the cart. Now let's see if we can work out from this what happened. What I've got is it was stationary. It had a slight curve here where I gave it a push. It then moved at near constant velocity. This is not a straight line, it's slowing down slightly. It hit the buffer at the other end and it came back, and again it's slowing down slightly, and because it passed the point of where I pushed it from, I didn't start at the beginning, we've gone back off. Let's look at this one again, and this time I'm going to wind the cart back to the beginning of the track. And I'm going to look at the camera this time so we can see the cart. Now, what I'm not very good at doing is pressing the button so we can see multiple screens at the same time. So we can do that, but it's much more difficult. No, we're alright, we'll manage it next time. We'll manage it next time. And what we're going to do is I'm going to press the record button. The software's recording, and we'll give it a push. Hits the buffers, comes back, and I'm going to stop the software. And we've got the same graph as we had before. We started, I gave it a quick push, and here we've got this distance time graph. It then bounces, comes back and slows down and returns back to the position it started. One of the toys I've got on this is that I can actually determine the slope of a line. So if I put the slope here on here, we can work out that when it started it was going 0.6391 meters per second, and gradually it slowed down, and on its way back it's doing 4, 4, 6, 4, 5, and you can see it is gradually slowing down as we move it along. We can see that also with the arrows. I'm going to push it much slower this time. So let's go back and watch it move. So I'm going to start this, but I'm going to give it a much gentler push. And you can see the velocity arrows giving us an indication of how strong I've pushed it. So let's start software recording. And let's give it a gentle push. 4 arrows going along, gone down to 3, bounces back, it's now only on 2, down to 1, and it might just about make it. No, it's not. And let's stop the software recording. And we can see this journey going on. So that is describing exactly what we've seen. Let's do this again a bit faster and repeat the first experiment, but this time I'm going to change this, so we're going to record the velocity and see what happens when we look at the velocity. We'll watch it first and then we'll see what the graph does. So we've got my little cart. And Paul's put up the graph for us, so I'm going to click here, record, and let's give it a push. And you can see it's slowing right down. It's not going to make its way back to the starting point. And that gave us the same graph we had before. I will give it a harder push this time. Let's repeat this. Much faster. And we're coming back. And we're just down to 4. Let's stop it. Let's see what happened if I had recorded instead of the position and the time, we'd recorded the velocity. And our velocity time graph looks very different. Let's have a look and see if we can work out what's happening. It's not moving. There's a slight acceleration as I gave it a quick push, and then it should have worked at a constant velocity. So this is our acceleration, not much time here, and this is my constant velocity moving along here, and that should be a nice straight line running along here. Now it's not. Why not? Because my machine is actually slowing down. Why? Because we've got some friction. Then it hits. We've got a sudden change in velocity going from one direction, now we're going to the other. It's got a constant velocity, which it isn't because it's slowing down very slightly, and then it hit my hand and we had virtually instantaneous deceleration and it stopped. So stopped, acceleration, constant velocity, which it isn't, stopping and starting again, the bounce, constant velocity, which it isn't, it's slowing down, and then me stopping the cart fairly quickly and it being stationary again. So we've got here my velocity time graph and also my position time graph, and we can see that we get some interesting sort of events going on here. One of the experiments that I like doing with many of my students is I turn them into the carts, and what I can do is set up an ultrasonic sensor and it can measure the distance. I'm using different carts today that can actually send out their own data, but we could send out the data via ultrasonic or whatever we want to. We get the same results. So we're getting, as we do this, one of these displacement time graphs. I've got the wrong, there we are. And what we've got for the displacement time graph is typically, what I would hope, a straight line. As the distance is moving, going away, we're moving at a constant velocity. They don't have to be like this, and rarely are they. We might throw something up in the air, and if we throw something up in the air, then we get a different type of graph made. If I were to perhaps take a distance time graph and I were to throw my trolley in the air, the velocity is going to be high, then it's going to slow down till it reaches a stop, and then it's going to come down. Trying this with the real trolley is a much more frightening prospect of an experiment, but we can achieve this. What I'm going to do is we're going to look at the trolley, and what I'm going to do is throw it up and down, and we're going to see if we can watch the software record this. So Paul's going to put on the graph, and what I'm going to do is challenge Paul to watch me throw the trolley up in the air and it come down. Now, just to make life easier, I'm going to throw it up in the air and go down. You'll see that we might get some arrows do something. We might. Let's see if I can record this. So if I throw it up in the air and down, are we going to get any results? No. Then why not? I've got the trolley going up and down. I can have it going left and right, in and out. But it's not going to record what I want to do. Now why not? Well, this trolley, it's measuring what happens with the wheels. I'm trying to show you the wheels. I'm trying to look at the screen and look at everything going. And it's only by doing the wheels that we're getting some movement. So if we want to try this type of experiment, we've got to try and do this with different sensors. If I go on to this screen, which I'm just going to stop, then what I have got, looking at my hardware setup, I've got cart position, we've got the acceleration sensor, I've got a gyro, and I've got my vector. And I've got all of these turned on at the moment. We can choose to work out my acceleration in a particular direction, and we can record my angular velocity. Whoa, that was exciting, in one direction or another direction or another direction. So let's try and see what happens. I'm in the X direction here, so let's see what happens to my cart when I pick the cart up and which button do I want to press? That one? Yeah. So we've got both. Now, if I pick this up and down, we can see that we're getting some sort of measurement. It's not easy to do this, to throw it up in the air and catch it. But what we will get, if I stop this to have a look, is we've got the idea of that graph. Now, I can't make it do this very well. I didn't intend to try and get it to work very well, because I need to throw it a lot higher to make it work. And I don't like dropping the cart too much. It's fairly indestructible, but I don't want to push my luck too much. So getting a graph looking like this one is a bit more difficult to achieve, because here we're going to need different equipment to try and do it. If we look at what's actually going on, and we've got a curve, and let's do this one with a distinctive curve again. So what I'm going to do is go to the camera let you see what's going on as well. And we're going to go back to measuring the position. You see my position there was always recorded as well. Let's start recording and push this along. What we should see on this one is it slows down a little bit. Not really good. I'm going to do that one again. I'm going to do it a little bit slower this time. So let's start recording. And I'm going to push it a little less hard. Because what I want to get is it slowing down and slowing down and slowing down. And let's see if we can look at this. Now I've got some nasty sort of graph here that I want to try and have a look at. Let's just expand this, and I can see that I've got this curve. If I want to measure the curve, then this software is quite good because I can measure it at any particular point that I want to. Whereas if you need to try and do this, you've got to try and draw this and put a tangent in at this point. And that's not easy. But if we need to try and do that, you need to work out the average. This is going to work out the average for me. So it's quite good. Let's try the same thing, but I want to look at this now doing some acceleration. For doing this, I'm going to need to change the way the system works. And the way the system's going to work is we're going to have this trolley, and I'm going to replace this trolley with the other one, only for a simple technical reason. And what I'm going to do with this trolley is I'm going to accelerate it down along the track, and it's going to hit the end and stop, and probably hopefully come back. This is my magnetic buffer, and what I'm going to do is I'm going to take a little wheel here, it's a pulley, and this pulley really does almost be sort of frictionless. So I'm going to put this on the end here, and I'm going to take a small weight. This is about 20 grams, and let's tie a string into the trolley, and at the other end we're going to tie the weight to the string. Don't quite have long enough arms to do this. When I let go of the trolley, the weight's going to go down, and the trolley is going to be accelerated by the force of the weight hitting the ground. And we have a slight problem. There we go. I've got this sorted. Right, okay. My assistant is actually going to release the trolley for me, because I can't do this. Can you take it back just a little bit and hold it? There's our mass on this end, and what I'm going to do is we're going to release this and we're going to measure just at the moment the position. So we're ready on the recording, and Paul's going to let go now. And let's stop. Now there's a little tight problem there because I recorded the blue cart. Little problem really there. I should have recorded the red cart. We'll do this again because although I did do it and it did work and I did record it, I didn't show it to you. So what we're going to do is do it again. Right, so we're back up here, the weight is at the top, the weight's going to fall down, hit the ground, and the trolley will then cease to accelerate and then carry on at constant velocity. Let's do this again. So I've got my red trolley, here we go, fire. And we'll stop. Let's look at this graph in detail. What we've got is it's stationary, then we've got a pull here, and at this point it seems to have more or less stopped accelerating, and we're then on a constant velocity. Let's look at a velocity time graph of this. And here we have our acceleration, and then it's starting to slow down, and then I stopped it and it bounced and it did various other bits and pieces. Looking at our acceleration, then our acceleration graph is constant. We have a massive change in acceleration, then a more or less constant acceleration, and then that stopped, and then all sorts of peculiar things happened because it reached the end. So we're expecting this line to be straight as an acceleration versus time graph, but it's certainly not. We can measure what it is. I can measure my acceleration, and it's about 0.054 meters per second. And it's varying quite a lot as we're going along. I'm just trying to find a place where it's more or less level. And there's our approximate acceleration. If I do this looking at the velocity graph, then if I look at my change in velocity, then here we can see perhaps a little bit clearer the acceleration here, and it's decelerating there. And if we look at a graph of this time distance and time, then if we look at this, we can see that our acceleration is just our change of velocity. So I can work out what my velocity is here, and I can work out what my velocity is here, and we can work out my change of velocity. It's still accelerating all the way up to there, so there's my acceleration over time. Let's take a time difference, so I could look at this point here, what my velocity is. So let's look at that one, and this is at a time of 3.5 seconds, and basically at, forgot to do the thing, 3.5 seconds we've got here at 0.6876 meters per second. At 4.5 seconds, then I can move this up here, this line, and see that at 4.5 seconds, that didn't help, I moved it, 9398. So if I look at my formula, my acceleration here is going to equal my change in velocity. So I've got my final velocity, which we're going to label V. I've got my initial velocity here, which I've set at U. And I've done it where we've got a constant amount of acceleration. The time is 1 second, so I've got 0.9398 minus 0.6876, all divided by 1, so I can ignore my 1, and I can work out this on my calculator. So I've hidden the software to calculator. And we could calculate this .9398 minus 0.6876. And that's going to give me here my acceleration of 0.2522 according to this. And if we look at the actual experiment where we're looking at the velocity, then I've got here a bit of a different reading. Such is life. Working on my acceleration, then it's giving me again try to grab hold of my line. Round about here we've got some sort of point number, which is probably, I worked out you were looking at the wrong screen than I was. We've got the number coming in here. So it's where we actually try to measure it from. I'm trying to measure across a large distance on my graph. I'm trying to measure from about halfway up to the full way, and it's slightly different. Right, okay, so we've looked at speed, we've looked at velocity, and we've got some idea of acceleration. And this was a fairly uniform acceleration. And we can use here my simple formula, which is the one I didn't write down. Acceleration equals V minus U over T. The change in acceleration with respect to time. Now, what happens if we've got acceleration that is changing? And we're seeing that in this experiment. I chose a bit of the line where hopefully it was not changing too much. Let's see what happens if we look at this experiment where we're going to make it change quite a lot. So if we take this cart and instead of putting on I've got 20 grams here. We can put on a bit more. I don't want to go above 30 really, because my cart doesn't seem to be able to cope with that. Right, we'll manage to tie it to the kitchen. So this is going to accelerate faster because we've got a greater force on this side.
So let's have
a look at what we're going to do. We've got the software ready. I'm going to measure position this time. I'm going to record all of them. I'll look at all the graphs. So we've set this ready to go, and Paul's going to let go. This time we can see that we've got a much larger curve. Let's just spread this out a little bit more. And we can see we've got really quite a curve from this point to about there. After that, it's relatively constant. And I can prove that by bringing in my little line, and it's staying more or less the same there, but here it's starting to change an awful lot. This is my position. Let's look at my velocity graph, and we have got relatively constant acceleration because this is due to gravity. But what would happen if we could try and take this and do it differently? Let's have a go. What I've got is a little fan. And what I'm going to try and do is I'm going to try and put my fan onto my cart. I'm going to give the cart a fighting chance. I'm actually going to take the string off. And what I'm going to do is wire this up. So I'm going to connect my fan to the cart, and I'm going to turn it around the other way, and the reason I'm going to turn it around the other way is so that I'm going to give it some buffers so when it hits the other side. I've got my fan now. I can switch my fan on. So we're on low power. Let's try it again. So it's working. Let's take my cart. I'm holding it still at the moment. And let's start the software. And we release the cart. And Paul's just going to pass it back down to me. And we'll switch the motor off. Let's have a look and see what happened in this graph. Well, it didn't accelerate very quickly. We can change this, and you can see that we've got a beautifully non-uniform acceleration here. This is anything but a straight line. Now, what's causing all this problem? Well, what's causing the problem is the fact that it's not accelerating nicely. We can look at this and we can see that it really is going all over the place. I really don't want to have a look at the acceleration graph, but we will. And if we look at this acceleration graph, let's just bring it down and let's change the scale, and you can see that we have got an extremely odd form of acceleration. Why? Well, it's all to do with the fan that's causing the problem. If we watch this move, and I want that one on, we can see
that it really isn't moving terribly steadily. Push it down.
We saw that on power 1. Let's try this on power 2. Can we get anything any better? And I'm going to record again my position. And had a bit more force that time. And we've got a different shape curve. If we look at the velocity, it's looking better. And if we look at the acceleration, this is looking better than it did. When it's slow and when it's fast, are slightly different. We can do this one more time. And I'm just going to go back to my position. And let's this time record it. I'm going to show you both pictures.
So it's going. Let's set this fan going a bit faster. 1, 2, maximum speed. Here we go.
And I actually did a very good job there because I managed to unplug the camera trying to catch the trolley. Well, I had a choice of catching one or the other. Would you want to do it again? Okay, my son says we're going to do it again. He's going to try and catch the trolley so you can see it. Let's have another go. So, we've got that camera on, we've got the screen on, and let's try it again. Right. Here we've got a different type. Let's see what we've got. I'm just trying to change this down a little bit. And here we've got a better sort of gradient that we can actually look at. And there it's a much more curved and uniform type of non-uniform acceleration. It's not going at the same rate all the time. We are actually getting some change on our position. Looking at our velocity, it's still fairly straight. It's curving in a little bit, And if I look at my acceleration, then we can see that yes, it is going down very slightly. I wouldn't like to live on the difference here. And it's still got these variations in it. So we're looking at acceleration and playing around with this about motion in a straight line at a constant acceleration. If we start playing around with some of these, and especially if you do maths and you do some differentiation and integration, you can have a look at how some of these work. But let's see what we've got. We've got then the fact that acceleration equals v minus u over t. I can rearrange this quite happily to say that my velocity is u plus at. Now we know that displacement, the s, the distance travelled, is the average velocity times the time taken. And because we know that, and we know that s equals vt, then we can get that s is going to equal u plus v times t divided by 2. If we combine those equations and do a bit of elimination, and I'm not going to do it, we can get s equals ut plus a half at squared. The fourth one is quite useful by combining these two together in another way. We can get that v squared equals u squared plus 2 times the acceleration and the distance. And this is SUVAT, because we've got distance, initial velocity, final velocity, acceleration and time. And these give rise to lots of questions that we can actually try and work out, and especially when you come to do mechanics in maths, we can get quite a lot of equations here to play with. What I've tried to do with this is give you some idea about how acceleration, velocity and position work and how they relate together. We can look in more detail about how this works, especially trying to drop an object. But before I do that, I've actually got to assemble my freefall equipment, and that's going to take me a day or so of Lego building to try and achieve a way we can do and measure freefall. So until then, stay safe. If you found this useful, then please subscribe, and I'll get back to my Lego making, and I'll see you same time next week to look at freefall. Thanks for watching.